Now that silence might sound like an absence of something, but before tonight concludes, you're going to recognize why it's much more than that. The silence has implications, 2 sets of them, in fact, and neither one is comforting. One of them means we are an extraordinary accident in an otherwise empty universe. The other means something has been ending civilizations before they get the chance to be heard, and we are next in line to face it. Let's start with what you think you already know about how big the universe is, because you almost certainly underestimate it. Most people have heard that the universe is vast. They've seen the diagrams, the photos from the Hubble telescope, the comparisons that try to put cosmic scale into human terms. And still, the numbers don't land the way they should. So let's actually try to make them land. The observable universe contains somewhere around 2 trillion galaxies, not 2 trillion stars, 2 trillion galaxies. Each one of those galaxies contains, on average, hundreds of billions of stars. Our own galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars, and it is a fairly average-sized galaxy. Not remarkably large, not remarkably small, just one of 2 trillion. When you try to calculate the total number of stars in the observable universe, you get a figure larger than the number of grains of sand on every beach and ocean floor on Earth. The numbers become almost impossible to hold in your mind. Now, let's zoom in. Let's forget the rest of the universe for a moment and focus exclusively on our own galaxy. The Milky Way alone contains between 100 and 400 billion stars. For decades, we had no idea how many of those stars might have planets. We guessed, but we didn't know. Then the Kepler Space Telescope changed everything. Kepler spent years staring at a small patch of sky, watching stars for tiny dips in brightness that would indicate a planet passing in front of them. What it found was staggering. Planets are not rare. Planets are ordinary. Most stars have them. Using Kepler data, astronomers now estimate there could be up to 300 million potentially habitable planets in the Milky Way alone. 300 million worlds in our galaxy that might support liquid water, that might have the right temperatures, that might have conditions where life as we understand it could exist. And beyond that, estimates suggest there could be as many as 6 billion Earth-like planets orbiting Sun-like stars in the Milky Way. 6 billion. In one galaxy out of 2 trillion. Here's where things get uncomfortable. Our Sun is about 4.6 billion years old. The Milky Way contains stars that are 8, 9, 10 billion years old. Some of the stars in our galaxy formed billions of years before our Sun even existed. If any of those older stars have planets in their habitable zones, and the numbers strongly suggest many of them do, then whatever life may have developed there had a head start of billions of years on us. Think about what that actually means. Modern human civilization, as we count it, is roughly 5,000 to 10,000 years old. We went from stone tools to radio telescopes in an eye blink of geological time. Now imagine a civilization that had that same capacity for technological development, but started 4 billion years earlier. Where would they be? What would they have built? What could they have done with 4 billion extra years of scientific progress? If a civilization anywhere in the Milky Way developed interstellar travel even at a tiny fraction of what physics might permit, even at speeds far slower than light, the math becomes difficult to ignore. At speeds achievable with technologies we can at least theoretically describe, a civilization could cross the entire Milky Way in somewhere around 1,000,000 years. 1,000,000 years sounds like a long time. In human terms, it is. But the Milky Way is 10 billion years old. 1,000,000 years is 1/10,000th of our galaxy's current age. In cosmic terms, it's nothing. It's the time it takes to blink. So here is the situation you're left with. A galaxy 10 billion years old, containing hundreds of billions of stars, with hundreds of millions of potentially habitable worlds, and some of those worlds circling stars that formed billions of years before our sun. If intelligence arises with any regularity at all, civilizations should have come and gone and spread and colonized across the entire Milky Way many times over before our planet even formed. The galaxy should be saturated with the evidence of advanced life, megastructures, signals, transformed star systems, something. And yet when we look out, we find nothing. No signals, no structures, no signatures, no visitors. The sky is quiet in every direction and at every frequency we've thought to check. We have pointed our most sensitive instruments at thousands of stars and millions of galaxies, and the silence is absolute. You could look at those numbers, 300 million habitable planets, 2 trillion galaxies, 10 billion years of cosmic history, and conclude that the universe is almost certainly full of life. The math seems to demand it. The statistics seem to make solitude nearly impossible. And then you look at what we've actually detected, and you find nothing at all. That gap between what the numbers say should be there and what we actually find when we look is the Fermi Paradox. It is not a minor discrepancy. It is not something that can be explained by saying, we haven't looked hard enough. It is a chasm, a silence so deep and so total that it demands an explanation. And that is what makes everything that comes next so deeply, profoundly disturbing. In 1961, a radio astronomer named Frank Drake sat down and tried to do something almost absurdly ambitious. Put an actual number on how many other civilizations might be out there. Drake was preparing for a small, unusual meeting at the National Radio Astronomy Observatory in Green Bank, West Virginia, the first gathering of scientists who were willing to treat the search for extraterrestrial intelligence as a legitimate scientific enterprise. There were 11 people in the room. Drake wanted to organize the discussion, so he wrote an equation on the blackboard. He wasn't trying to solve the problem. He was trying to structure it. What he ended up creating was one of the most discussed and argued over formulas in the history of science. The Drake equation doesn't give you a single answer. That's not what it's for. What it does is break a nearly impossible question into smaller, more manageable pieces. How many communicating civilizations exist in our galaxy right now? That's the question. And instead of throwing up your hands, Drake said, let's figure out what we'd need to know to answer it, and then let's estimate each piece as carefully as we can. Multiply the estimates together, and you get a number. The equation is a framework for thinking, not a calculator for certainty. So here's what goes into it. First, you need to know how fast new stars are forming in the Milky Way. This one we know reasonably well. Astronomers estimate it's somewhere around 1 to 3 new stars per year. Then you need the fraction of those stars that have planets orbiting them. A few decades ago, this was genuinely unknown. Now, after the Kepler Space Telescope surveyed a patch of sky and found planets almost everywhere it looked, the scientific consensus has shifted dramatically. The fraction is high, probably close to 1. Most stars have planets. Next comes the fraction of those planets that sit in what's called the habitable zone, close enough to their star for liquid water but not so close that it evaporates. Current estimates put this somewhere between a fifth and a half of all planetary systems. Then you need the fraction of habitable planets where life actually emerges. This is where the equation starts to get genuinely uncertain. We have exactly one example of life arising: Earth. That's not enough data to calculate a probability. Some scientists argue that because life appeared on Earth very quickly after conditions allowed it, life must emerge readily wherever conditions are right. Others say we have no idea. Drake himself was optimistic. Many modern researchers are more cautious. After that comes the fraction of living worlds where intelligence eventually develops. Again, one data point. One species on one planet with anything resembling our kind of problem-solving, language, and technology. Then the fraction of intelligent species that develop the kind of technology capable of sending detectable signals into space. And finally, and this is the variable that makes everything else almost irrelevant depending on how you set it, the average length of time a technological civilization remains detectable. If civilizations typically broadcast signals for 1 million years, the galaxy could be full of them. If they typically destroy themselves within a few centuries of developing radio technology, the number drops towards 0 almost immediately. This last variable is less an astronomical question than a civilizational one. And it's haunting precisely because of that. Here's the thing most people don't realize when they first encounter this equation. Even if you plug in pessimistic values for every uncertain variable, even if you assume life is rare, intelligence is rarer, and technological civilizations are rarer still, you can still end up with a number well above 1. The universe is simply too large, and the Milky Way too ancient, for the math to easily produce 0. Run it with cautious assumptions and you might get dozens of civilizations. Run it with moderate optimism and you get thousands. Run it the way Drake did in that room in Greenbank in 1961, with the best estimates he had available, and you get a number somewhere between 1,000 and 100 million civilizations broadcasting signals in our galaxy at this very moment. The uncertainty in the equation is real, and scientists take it seriously. We're guessing at several of the variables with almost no hard data to anchor us, but that uncertainty cuts in both directions. You can't use the uncertainty to argue the answer is probably 0. Across the full range of reasonable assumptions, the equation keeps returning the same uncomfortable conclusion. We should not be alone. The numbers almost refuse to produce solitude, and yet here we are, surrounded by silence. By almost any reasonable estimate, the answer should be hundreds, possibly thousands of civilizations capable of making contact with us right now. So if the numbers say we should be surrounded by other civilizations, here is the obvious question: where are they? That question has been the driving force behind one of the longest, most ambitious scientific projects in human history. In 1960, a radio astronomer named Frank Drake, the same Drake from the equation, pointed a 26-meter radio telescope at 2 nearby sun-like stars and listened. The project was called Ozma. It ran for about 200 hours. It found nothing, but it established something important. This was a real scientific question, and radio telescopes were a real way to pursue it. The logic was straightforward. Radio waves travel at the speed of light. They're cheap to produce, Any civilization advanced enough to build the technology we have right now could be broadcasting into space, and we could, in theory, detect it. So we started listening. What followed was 6 decades of increasingly sophisticated searching. The SETI Institute, formally established in 1984, became the institutional home for much of this work. Researchers there and at universities around the world have used some of the largest radio telescopes ever built, including the Arecibo Observatory in Puerto Rico, which had a dish 305 meters across, to scan the sky across millions of different frequencies. The idea is that you don't know which frequency an alien civilization would choose to broadcast on, so you try to cover as many as possible. Modern systems can monitor hundreds of millions of frequency channels simultaneously. That's a genuinely staggering technical achievement, and it's improved by orders of magnitude from where things stood in 1960. The search expanded beyond radio as well. Optical SETI programs scan the sky for brief, intense laser pulses. Another way an advanced civilization might send a signal across interstellar distances. Then there was SETI at Home, a computing project launched in 1999 that asked ordinary people to donate their personal computer's idle processing power to help analyze data from radio telescope observations. At its peak, it had over 5 million users across 226 countries. It was one of the largest distributed computing projects ever attempted. Researchers could process far more data than any single facility could handle on its own. The project ran for over 20 years. Now here is where the story gets genuinely strange. In August of 1977, an astronomer named Jerry Eman was reviewing data from Ohio State University's Big Ear radio telescope. He found something that stopped him cold. A signal had been detected at almost exactly the frequency that scientists had theorized an extraterrestrial civilization might choose to broadcast on. 1420 megahertz, the emission frequency of hydrogen, the most abundant element in the universe. The signal lasted 72 seconds, the full window during which the telescope could observe it. It was strong. It had the shape and profile that researchers had predicted an extraterrestrial signal might have. Eman circled it on the printout and wrote one word in the margin: wow. That's what we still call it, the wow signal. Astronomers have pointed telescopes at that patch of sky hundreds of times since 1977. The signal has never appeared again. No explanation has ever been confirmed. It remains unexplained to this day. That's the story of SETI in miniature. A moment of electrifying possibility, and then silence. So what has all of this searching actually found? We've now surveyed thousands of stars in careful, detailed observation, and millions more at lower resolution. We've scanned across vast swaths of the sky at frequencies and sensitivities that would have seemed impossible to researchers in 1960. No confirmed signal of extraterrestrial origin has ever been detected. Not one. Not a stray pulse. Not a repeating pattern. Not even an anomaly that held up under scrutiny. The wow signal is the closest thing we have, and it has never come back. Here's the counter-argument you're probably forming right now. We haven't looked long enough. The universe is enormous. 60 years of searching is barely anything on a cosmic timescale. We've only examined a tiny fraction of the stars in the Milky Way in any real depth. Maybe we're just not being patient enough. Scientists take this seriously. It's not a bad objection, But here's the thing most people don't realize about the scope of what we've actually done. We've surveyed millions of star systems. We've covered enormous ranges of the electromagnetic spectrum. We've built tools sensitive enough to detect the kind of signals we ourselves produce from distances of dozens of light years. And the silence isn't partial. It isn't ambiguous. It's complete. 60 years of listening, with increasingly sensitive equipment pointing at increasingly large portions of the sky, and the answer has been the same every single time: nothing. In 1996, an economist and researcher named Robin Hanson published a paper that made physicists, biologists, and anyone who read it carefully deeply uncomfortable. The paper wasn't long. It wasn't filled with complex mathematics or dense technical jargon, but the logic inside it was almost impossible to argue with, and the conclusion it pointed toward was genuinely disturbing. Hansen started from the same place everyone starts. The universe is enormous, it's ancient, and the numbers suggest it should be full of advanced civilizations. And yet, as we've established, it isn't. The sky is quiet, no signals, no megastructures, no visitors. So Hansen asked the obvious follow-up question: why? And here's the thing most people don't realize. The answer he arrived at isn't just uncomfortable in the way that unsolved mysteries are uncomfortable. It's uncomfortable because the two possible answers are both, in their own ways, terrifying. His argument was straightforward. If life has a natural tendency to evolve from simple chemistry into galaxy-spanning civilizations, we should see evidence of those civilizations everywhere. We don't. So something is stopping it. Something in the chain of steps between lifeless chemistry and interstellar expansion is almost impossibly difficult to get through. Hansen called it the Great Filter. Not a filter in the casual sense, but a barrier so severe that virtually no species in the history of the universe has ever cleared it. Something that sits in the development of life and civilizations like an almost impassable wall, and the overwhelming majority of everything that ever tried to get through it didn't make it. To understand why this is so unsettling, you need to think about what biologists call a hard step. A hard step is a transition in evolutionary history, so unlikely that even given billions of planets and billions of years, it might only happen once, maybe twice. These aren't transitions that are merely difficult. They're transitions that require such a specific and improbable sequence of events that probability alone suggests they shouldn't happen at all. And yet on Earth, clearly, something kept stumbling forward anyway. Now, let's walk through the chain of steps that got us here. First, you need the right chemistry. Organic molecules, carbon-based compounds capable of doing interesting things. That seems to happen readily enough. We find organic molecules in meteorites, in interstellar clouds scattered across the solar system. Then, somehow, those molecules have to organize themselves into something that can copy itself. That's the origin of life, what scientists call abiogenesis. We have no idea how probable that step is. We have exactly one confirmed example. From there, early single-celled life has to persist and survive for long enough to take the next step. On Earth, that took roughly 2 billion years. Then comes the transition from simple cells to complex cells. Cells with internal structure, with nuclei and mitochondria. Another enormous leap. Then multicellular life, where individual cells begin cooperating to form larger organisms. then organisms complex enough to develop nervous systems, and then brains. Then social creatures capable of learning from each other and passing knowledge forward. Then intelligence. Then technology. Then the capacity to leave your home planet entirely. Every one of Ho's transitions is a step. The great filter is somewhere in that chain. And that's where things get genuinely uncomfortable. Here's the thing. We don't know which step it is. We can't look at the chain and point to the step that almost didn't happen. From where we're standing, having made it through all of them, everything in the past looks survivable by definition. And that's the problem. Because the great filter could be behind us, meaning we've already passed through the near impossible part and the road ahead is open. Or the great filter could be ahead of us, meaning the catastrophic bottleneck is still coming, and every civilization that has ever reached our level of development has been destroyed by it. Think about that for a second. Either we are extraordinarily lucky, the cosmic exception, the species that somehow threaded a near impossible needle, or we are exactly as ordinary as we feared, and what's waiting for us is the same thing that has silenced every other civilization that ever existed. There is no third option that feels good. Even the hopeful version of this story carries its own weight. If the filter is behind us, and we are genuinely rare, that means we may be the only technological civilization in the observable universe. All of this, all of the cosmos, and the only place where anyone has ever asked a question or built a machine or looked up and wondered is right here. That's a lonely and crushing kind of luck, and if the filter is ahead of us, then right now, we are somewhere in the sequence of steps that precedes it. We are, in a sense, approaching something that has ended everyone else who has ever tried, not because the universe is hostile, but because something about the development of advanced life makes destruction almost inevitable. And the chilling implication of the silence is that it hasn't been survivable. Not once. Not yet. And the question of where exactly that filter sits, behind us, already survived, or somewhere ahead, is perhaps the most consequential question our species has ever had to reckon with. There are essentially two ways to interpret the great filter, and if you sit with both of them honestly, neither one is comforting. The first possibility is that the filter is already behind us, somewhere in the long chain of steps that produced you sitting here, capable of asking this question. Something happened that was so extraordinarily unlikely that it has essentially never happened anywhere else. Maybe it was the origin of life itself. Maybe it was the leap from simple cells to complex ones. Maybe it was the emergence of intelligence, or language, or the specific combination of factors that produced a species willing to point radio telescopes at the sky and wonder. Whatever it was, on this interpretation, it happened here, and almost certainly nowhere else. We are the accident, the improbable exception, possibly the only minds that have ever existed in the entire observable universe, and quite possibly the only minds that ever will. That is a lonely thought, genuinely, deeply lonely. The universe is roughly 93 billion light-years across and contains something in the range of 2 trillion galaxies. And if this scenario is correct, all of it is empty of anything that thinks or wonders or builds or hopes. Every star you can see tonight is orbited by worlds that are nothing but rock and gas and chemical silence. We are it. The whole of conscious experience, as far as the cosmos is concerned, fits on one small planet around one unremarkable star. But here's the thing most people don't realize when they first encounter this scenario. As bleak as it sounds, it's actually the good version. If the filter is behind us, we made it through. Whatever nearly impossible transition destroyed every other chance at life before it could get started, we somehow cleared it. The road ahead might still be hard, but it isn't cursed. We are not walking towards something that has already killed everyone else. The second possibility is different, and it's worse. On this interpretation, the filter is not behind us, it's ahead. Life arises across the cosmos with some regularity. Simple chemistry becomes biology often enough. Organisms develop, complexity increases, intelligence emerges. Civilizations build telescopes and cities and weapons and eventually reach exactly the technological level we're at right now, and then something ends them. Something consistent. Something that has worked every single time, across every civilization that has ever reached this point, without a single exception that we can detect. Because if there had been a single exception, we'd see it. We'd see the Dyson spheres, the megastructures, the radio signals, the consequences of a civilization that got through. We see none of that, which means whatever the filter ahead looks like, it has a perfect record. Think about what that means. Every species that ever learned to split the atom, every civilization that ever pointed instruments at the night sky looking for others, every world that reached the moment we are in right now, gone. And we are not past that moment. We are in it. Now here's where the framework produces something that feels almost counterintuitive, but you need to sit with it. Most of us, if asked, would say that finding life out there would be wonderful news. Evidence of microbes on Mars, or signals from a distant star, or ruins of a civilization that once flourished somewhere in the galaxy. These feel like they should be cause for celebration. In any normal context, they would be. But in the context of the Great Filter, they are not good news. They are alarming news. They might be the worst news imaginable. Here's why. If we discover simple microbial life on Mars tomorrow, that tells us something specific. Life is not extraordinarily rare. Abiogenesis is not the filter, which means the filter is somewhere else in the chain, somewhere between a microbe and a civilization, somewhere we haven't passed yet. The closer the discovered life is to us, the worse the implication. Microbes on Mars would be unsettling. Complex multicellular life would be more unsettling. Ruins of an intelligent civilization anywhere in our neighborhood would mean the filter almost certainly lies exactly where we are right now, at the transition from a technological species to a spacefaring one. And no civilization has ever made it through. So when scientists who understand this framework look at the question of extraterrestrial life, they find themselves in a strange position. The universe they most want to live in, the universe where humanity has the best odds of a long future, is the universe that looks emptiest. Every piece of evidence for life out there shifts the probability of where the filter sits, and it shifts it in the wrong direction. This is not a comfortable place to end up. Most of us were raised on the hope that contact with another civilization would be one of the great moments in human history. The Fermi Paradox and the Great Filter don't just complicate that hope. They invert it. The empty sky, the radio silence, the absence of ruins or signals or megastructures, these things start to look less like a mystery and more like the best-case outcome. You find yourself hoping, with everything you have, that the universe is as empty and lifeless as it appears, because if it isn't, the implications for us are almost too bleak to think about. Let's consider the most hopeful version of the Great Filter first, the one that would mean we're not in danger, the possibility that the hardest step was at the very beginning, before anything resembling life existed at all. Here's what abiogenesis actually is. It's the process by which chemistry becomes biology, not metaphorically, literally. At some point on this planet, roughly 3.8 billion years ago, a collection of molecules crossed a threshold. They began copying themselves. They began evolving, and at that moment, for reasons we still cannot fully explain, life existed where none had existed before. We don't know how it happened. That is not an overstatement. After decades of research, some of the best chemists and biologists on the planet cannot tell you, with any confidence, how non-living matter became living matter on the early Earth. Think about what that transition actually required. You need organic molecules forming spontaneously from simpler chemical compounds. Those molecules then need to assemble into something far more complex, polymers capable of storing and transmitting information, something like RNA. And then, somehow, a system has to emerge that can copy that information, make errors in copying it, and pass those errors on to the next generation. That's the minimum. That's the floor. Before any of that, you have a barren, rocky planet with chemistry. After all of it, you have something that can, given enough time, eventually build a radio telescope. The gap between those two things is almost incomprehensible. Scientists have been trying to bridge that gap in the laboratory for over 70 years. In 1953, Stanley Miller and Harold Urey ran an experiment that genuinely seemed like a breakthrough. They simulated the conditions of the early Earth: water, methane, ammonia, hydrogen, and ran electrical sparks through the mixture to imitate lightning. Within a week, the apparatus had produced amino acids, the building blocks of proteins. The scientific community was electrified. Life's ingredients were appearing on their own. It seemed like the rest was just a matter of detail, but the details turned out to be everything. Amino acids are not life. They are not even close to life. Getting from amino acids to a self-replicating system is a problem that has resisted solution ever since. One leading framework is the RNA world hypothesis. The idea that before DNA and proteins, RNA molecules served as both the carriers of genetic information and the catalysts of chemical reactions. It's an elegant idea. It solves a chicken and egg problem at the heart of biochemistry, where proteins need DNA to form and DNA needs proteins to replicate. RNA can, at least in principle, do both, but no one has demonstrated a plausible pathway for RNA assembling itself spontaneously under realistic early Earth conditions and then organizing into a self-replicating system. It's theoretically possible. It has not been shown. Hydrothermal vent theories offer another angle. Deep-sea vents, where superheated water rich in minerals flows up through cracks in the ocean floor, create chemical gradients that could in principle drive early biochemistry. The chemistry is real. The energy is there. Some researchers believe alkaline hydrothermal vents in particular offer the right conditions for the earliest metabolic reactions to have emerged. But again, the full picture, from vent chemistry to life, remains undemonstrated. We can identify plausible environments, We can produce plausible building blocks. The actual assembly, the moment when things cross the threshold from chemistry to biology, has not been replicated. Here's the thing most people don't realize about our situation. We have exactly one data point: Earth. Life arose here, and we know it arose here because we exist. But knowing that it happened tells us almost nothing about how probable it was. Imagine you were the only person to ever win a particular lottery, and someone asks you how likely it is that people win lotteries. Your existence proves the lottery can be won. It tells you almost nothing about the odds. That is precisely the epistemic trap we're in with abiogenesis. We know it happened here. We have no idea if the probability was 1 in 10, 1 in a billion, or 1 in 10 to the power of a trillion. And if the probability is vanishingly small, if abiogenesis requires a sequence of chemical accidents so specific, so unlikely, so dependent on precise conditions, aligning in exactly the right way at exactly the right moment, then the great filter is right there at the beginning. It's not nuclear weapons. It's not artificial intelligence. It's not any danger we face as a civilization. It's simply that life itself is extraordinarily hard to start. Most planets stay barren, not because anything destroys the life that forms, but because life never forms. The silence of the cosmos makes sense not because civilizations rise and burn. It makes sense because the spark never catches. This would mean we are not one of many living worlds, with most failing to produce intelligence. We might be the only living world, period. The only place in the observable universe where that chemical threshold was crossed. Every other planet, every other moon, every other world orbiting every other star is exactly what it appears to be from a distance: rock, gas, ice, and chemistry, but nothing more. Now, there is one piece of evidence that cuts slightly against this. Life on Earth appeared relatively quickly after the planet cooled enough to support it. The window between a habitable surface and the earliest evidence of microbial life is surprisingly short in geological terms. Some scientists read that as evidence that, given the right conditions, life doesn't actually take that long to emerge. That the process, while complex, might be more robust than we think. It's a real argument, and it's worth holding on to. Maybe that's all there is to the cosmic silence, an extraordinarily improbable chemical accident that happened once, and we are the result, and the universe beyond us is simply lifeless rock and gas and void. But let's say abiogenesis is not the filter. Let's say life does arise with some regularity on planets that have the right conditions. Even then, you're nowhere near a civilization. You're not even close. What you have is chemistry that can copy itself, and that is genuinely remarkable. But it is also profoundly simple. And here's the thing most people don't realize. For almost half the entire history of life on Earth, that's all there was. Simple cells, bacteria, nothing more. To understand why the next step matters so much, you need to understand what a prokaryote actually is. Prokaryotes are the bacteria and archaea that have dominated this planet since life first appeared roughly 3.8 billion years ago. They are extraordinarily successful organisms. They survive in boiling hydrothermal vents and frozen Antarctic ice. They live in your gut, in the soil, in the upper atmosphere. If you measured life on Earth by sheer biomass, bacteria would still win. They are resilient in ways that almost nothing else is, and they have been evolving and diversifying for billions of years. But they are fundamentally, structurally simple. A prokaryotic cell has no nucleus. It has no mitochondria. It has no internal compartments of any kind. Its DNA floats freely inside the cell. The whole thing is essentially a membrane around a bag of chemistry, and that is it. Now compare that to a eukaryotic cell. Eukaryotic cells have a nucleus, a protected compartment specifically housing the cell's genetic material. They have mitochondria, which generate the cell's energy. They have a complex internal architecture of membranes and organelles, each performing specialized functions. Every plant on Earth is made of eukaryotic cells. Every animal, every fungus, every organism you can see with your naked eye. The leap from prokaryote to eukaryote is not a small refinement. It is an entirely different category of biological organization. So how did it happen? The leading explanation is called endosymbiotic theory, and it describes something that sounds almost accidental. At some point, roughly 1.8 to 2 billion years ago, one prokaryote absorbed another, not digested it, absorbed it and kept it alive. The two cells established a permanent partnership, and over enormous stretches of time, the absorbed bacterium lost its independence entirely and became what we now call mitochondria. It still carries its own DNA, distinct from the rest of the cell. It still divides on its own schedule. It is, in a very real sense, a bacterium living inside your cells right now. That merger is why you can exist. Here's where things get uncomfortable. That event may have happened only once. Not once per planet, not once per ocean, once in the entire history of life on Earth. Every eukaryotic organism that has ever lived, from the first complex cell to every tree, every fish, every human being, traces back to that single merger. There is no evidence of it happening a second time, and life had roughly 2 billion years to attempt it. 2 billion years of bacteria reproducing trillions upon trillions of times, encountering each other constantly, and this particular combination, the one that stuck, the one that held, the one that built toward complexity, happened once. Think about what that timeline actually means. Life appeared on this planet around 3.8 billion years ago. Complex eukaryotic cells didn't show up until somewhere between 1.8 and 2 billion years ago. That's nearly 2 billion years of nothing happening in terms of structural complexity. No progress toward anything we'd recognize as sophisticated biology. Bacteria became better bacteria. They became more diverse bacteria. But the fundamental architecture stayed exactly the same. And then something changed. A single improbable event occurred, and from that event came every complex organism that has ever lived. Now apply that to the broader question. If worlds with liquid water and basic chemistry can generate microbial life with some regularity, there might be billions of them out there. Mars may have had them. The moons of Jupiter and Saturn might harbor them. But if the step from simple prokaryotic cells to complex eukaryotic cells is genuinely near impossible, if it requires a specific sequence of events so unlikely that Earth needed 2 billion years to stumble into it accidentally, then most of those worlds are still sitting at the bacterial stage. Diverse, resilient, and completely stuck. The universe in this scenario is not empty. It might be teeming with microscopic life, but complex life, the kind that can eventually become multicellular, develop organs, build nervous systems, think, might be extraordinarily rare, not because conditions are harsh, but because the single structural innovation that makes complexity possible is just that difficult to produce. 2 billion years of stasis, and then a transition so radical that nothing remotely comparable has happened in the billion years since. And it may have only happened once on this planet by chance. Even if we grant that eukaryotic cells are possible and that multicellular life will eventually emerge from them, we're still a long way from a civilization capable of building a radio telescope. Multicellular life has existed on Earth for roughly 600 million years. That's an enormous span of time, and in all of it, technological intelligence has appeared exactly once. Think about what that means for a second. 600 million years of animals, plants, fungi, increasingly complex nervous systems, increasingly sophisticated behavior, and one lineage on one branch of one family tree figured out how to smelt metal and write equations. Just one. The dinosaurs are worth pausing on here. They dominated this planet for over 150 million years. They weren't simple organisms. Some species showed behavioral complexity, parental care, group hunting. They had more than enough time. 150 million years is so long that it's almost meaningless to say out loud. Modern humans have existed for maybe 300,000 years. The dinosaurs had 500 times that window, and nothing resembling technology ever emerged. They went extinct, leaving no tools, no structures built with intent, no evidence of anything beyond what biology alone could produce. And it's not just the dinosaurs. Look at the mammals that came after them. Whales and dolphins have been around for tens of millions of years, with large brains and complex social lives. Elephants have demonstrated remarkable problem-solving ability and what looks a great deal like grief. Crows use tools. Primates have been manipulating objects and solving puzzles for millions of years. None of them crossed the threshold into anything we'd recognize as technological civilization. That threshold, whatever it is, appears to be extraordinarily difficult to reach. Here's where things get uncomfortable. A large brain alone isn't enough. What intelligence actually requires, in the human sense, is a very specific combination of traits arriving together. You need social structures that reward sharing information across individuals, so that knowledge accumulates instead of dying with each person who learns it. You need hands capable of fine manipulation, the ability to hold, shape, and construct. You need an extended childhood, a long developmental window in which a young organism can absorb knowledge from the adults around it rather than relying entirely on instinct. You need language sophisticated enough to transmit abstract concepts. And you need something harder to pin down, a combination of curiosity and competitive drive that makes individuals want to understand and reshape their environment rather than simply survive in it. Remove any one of those factors, and the whole system probably doesn't produce a radio telescope. That's the point. It's not that brains are rare. It's that this exact configuration of pressures, anatomy, social structure, and developmental timing is rare. Each of those traits evolved for reasons that had nothing to do with building technology. They came together in our lineage almost accidentally, shaped by pressures specific to a particular environment in a particular period of Earth's history. There's no obvious reason to expect that same combination to reliably assemble itself on other worlds, even worlds with complex animal life. The octopus offers an interesting piece of evidence here. Cephalopod intelligence evolved completely independently from vertebrate intelligence, a separate experiment running in parallel on a completely different body plan. Octopuses can solve problems, recognize individual humans, navigate mazes, use objects as tools. Their intelligence is real, and it's striking. But there's a gap between what an octopus can do and what a technological civilization requires that is difficult to overstate. They lack the social structures that allow knowledge to accumulate across generations. They're largely solitary. They have no extended childhood. Most never meet their parents. Their lifespan is short. The raw problem-solving ability is there, but almost everything else required for technological development is missing. The octopus tells us that complex cognition can emerge through more than one evolutionary path. It doesn't tell us that the full suite of traits required for civilization will do the same. So let's put this together with everything that came before it. Life has to emerge from chemistry. That might be extraordinarily unlikely. Then it has to make the jump to complex eukaryotic cells. That might have happened only once in Earth's history and took nearly 2 billion years. Then it has to produce multicellular organisms sophisticated enough to develop nervous systems worth talking about. Then, from that enormous diversity of complex animal life, something has to stumble into the exact combination of anatomy, social behavior, developmental timing, and cognitive architecture that allows technology to accumulate across generations. 600 million years of trying, and it happened once. Every one of these steps might be rare in isolation, and their combination, a planet that threads every needle, billions of years in a row, might be so improbable that Earth is simply the one exception in an otherwise empty universe. Here's what makes the silence so much harder to dismiss than it might initially seem. So far, we've been talking about the absence of radio signals. No one is calling us. No one seems to be broadcasting. But here's the thing most people don't realize. Silence on the radio is actually the least troubling part of this problem. The much harder thing to explain is the absence of everything else. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a framework for thinking about what advanced civilizations would actually look like from a distance. Not what they might say to us, but what they would physically do to the universe around them. The Kardashev Scale ranks civilizations by how much energy they can harness. A Type 1 civilization controls all the energy available on its home planet, every joule from every source, fully utilized. A Type 2 civilization harnesses the entire energy output of its star. A Type 3 civilization commands the energy resources of its entire galaxy. We are currently sitting at roughly 0.73 on this scale. We are not yet a Type 1 civilization. We haven't even finished harnessing our own planet. Now think about what a Type 2 civilization would look like from across the galaxy. To use all the energy from a star, you'd need to surround it. Physicist Freeman Dyson described exactly this idea in 1960. A vast shell or swarm of structures enclosing a star, capturing its light before it can radiate away into empty space. This kind of megastructure is called a Dyson sphere, or in a more realistic configuration, a Dyson swarm. The star itself would become dim, possibly invisible at optical wavelengths. But all that captured energy has to go somewhere. The civilization using it generates heat, and that heat radiates back out as infrared light. So a Type 2 civilization star wouldn't disappear entirely. It would glow in a way that no natural process can explain. Unusually dim, anomalously warm, distinctly strange. A Type 3 civilization would be something else altogether. At that scale, you wouldn't just be modifying one star. You'd be reshaping clusters of them, consuming stellar energy across an entire galaxy. From intergalactic distances, you wouldn't need a radio telescope to detect a Type 3 civilization. You might see it with the naked eye. A galaxy slowly going dark as its stars are surrounded one by one, radiating waste heat across the infrared spectrum. Its structure altered by engineering on a scale we can barely conceive of. How long would it take a civilization to reach Type 3? At even modest rates of expansion, something on the order of a few million years. The Milky Way is over 10 billion years old. There has been time for this to happen here, many times over. So scientists went looking, not for radio signals, for megastructures, for the physical fingerprints of civilizations that had been engineering the universe around them. A research initiative called Project Jet, the glimpsing heat from alien technologies, systematically analyzed infrared data from nearly 100,000 galaxies. The logic was straightforward. If even a small fraction of galaxies hosted Type 3 civilizations, there should be detectable anomalies, waste heat, unusual infrared signatures, galaxies behaving in ways that stars and gas alone cannot account for. The researchers examined the data carefully, looking for anything that didn't fit the expected thermal profiles of natural stellar processes. They found nothing. 100,000 galaxies. No convincing evidence of a single Type 3 civilization anywhere in the sample. Closer to home, astronomers have scanned individual stars for signs of Dyson structures. In 2015, the star KIC 8462852, quickly nicknamed Tabby's star, became briefly famous because it dimmed in irregular, dramatic patterns that no one could immediately explain. For a moment, the possibility of a megastructure was taken seriously by researchers. It made the news. People paid attention. Further study pointed toward more mundane explanations, likely clouds of dust. But the episode revealed how unusual it would be to actually find something. We were excited by an anomaly. We have not found the anomaly repeated elsewhere, at any of the millions of other stars we've examined. That is the thing worth sitting with. We've surveyed enough of the sky with enough sensitivity that the absence of megastructures is no longer just a gap in our data. It is a result. The universe has been observed, and it does not contain the visible signatures of advanced technological life, not locally, not in distant galaxies, not anywhere we've pointed our instruments with sufficient care to know the difference. We're not just failing to hear voices from across the cosmos. We're failing to see any light that shouldn't be there, any megastructure, any galaxy slowly going dark as its stars are surrounded and harvested, any sign at all that anything out there has ever done anything. Not everyone who thinks seriously about the Fermi Paradox lands on the Great Filter, and it's worth sitting with the alternatives before deciding how seriously to take them. The first is called the zoo hypothesis. The idea is that advanced civilizations are out there, They know we exist, and they've made a deliberate choice not to contact us. Think of it like a nature reserve. A researcher studying a wolf population doesn't walk into the forest and introduce herself. She watches. She documents. She keeps her distance precisely because interference would corrupt what she's trying to observe. Under this hypothesis, Earth is the preserve. We're the wolves. And every civilization advanced enough to reach us has agreed, for ethical or scientific reasons, to leave us alone until we develop further on our own terms. It's a generous interpretation of the silence. It assumes the universe is populated by patient, principled observers who respect our autonomy. And honestly, it's not a crazy idea. We have our own version of this logic. When biologists study uncontacted tribes, the standard position is non-interference. You could argue that any civilization wise enough to survive long enough to find us would have developed similar principles. But here's the thing most people don't realize when they find this explanation comforting. The zoo hypothesis doesn't just require one civilization to agree to stay silent. It requires every civilization to agree. All of them. Across billions of years and unimaginable distances. Every single one. Because all it takes is one. One curious species. One rogue explorer. One civilization that decides the ethical framework doesn't apply to them, and the silence breaks. The hypothesis only works if the coordination is perfect and permanent. That's an extraordinary assumption to make about beings we've never met. Then there's the communication gap argument. Maybe we're listening on the wrong frequencies entirely. Radio waves are what we understand, so that's what we search for. But an advanced civilization might have moved on from radio the way we moved on from smoke signals. They could be communicating through gravitational waves, neutrino beams, quantum entanglement, or methods we haven't conceived of yet. The signals might be flowing through our solar system right now. We'd have no way to know. This one deserves to be taken seriously. It's genuinely possible we're pressing our ears against the wrong wall. But the problem is that our searches have expanded dramatically over the decades. We're not just scanning a handful of radio frequencies anymore. We're covering wider bands, using optical telescopes to search for laser pulses, and developing new detection methods steadily. And as the search expands, the silence expands with it. At some point, the communication gap explanation starts to require that we've somehow managed to miss every single method that every civilization has ever used, across every star system we've observed. That becomes a harder and harder position to defend. The timing argument is more subtle. It goes like this. Maybe a civilization transmits signals for 100 years and then stops, either because they develop more efficient communication or because they're gone. The window when their signal is detectable is narrow. The window when we happen to be listening with the right equipment is also narrow. The overlap between those two windows, multiplied across billions of stars, might be vanishingly small. We might simply be out of sync with everyone. There's something to this. The math isn't unreasonable on its face, but when you actually run the numbers, accounting for the billions of stars and billions of years involved, even a modest rate of civilizations transmitting for short windows should produce some detectable overlap. The complete absence of any signal strains the timing argument to its limits. And then there's the planetarium hypothesis. We live in a simulation, or a constructed reality, and whatever built it simply chose to populate our observable universe with the appearance of emptiness. This one is genuinely unfalsifiable, which makes it more philosophy than science. You can't rule it out. You also can't do anything useful with it. What all of these explanations share is a certain quality of relief. They let you believe the universe might be full of life without requiring you to confront what the silence actually implies. They're appealing ideas because they don't require us to be in danger, but the more carefully you examine each one, the more it starts to feel like wishful thinking dressed up in scientific language. There's another explanation for the silence that has gained serious attention in recent years, and it is in some ways even more unsettling than the Great Filter itself. It doesn't require a filter at all. It doesn't require civilizations to be rare or to destroy themselves. It requires only that civilizations are rational, that they understand their situation clearly, and that they act accordingly. If that's the case, the silence isn't absence, it's strategy. This is the dark forest hypothesis. The name comes from Chinese science fiction writer Liu Cixin, who used it as the organizing logic of his three-body problem trilogy. But the reasoning behind it isn't fiction. It's game theory applied to the cosmos, and when you follow it to its conclusion, it is genuinely difficult to dismiss. Here's the core logic. The universe contains finite resources. Stars burn out. Planets are only so numerous. Any civilization expanding across the cosmos is competing, whether it intends to or not, with every other civilization doing the same. Now add one more condition. You can never fully verify another civilization's intentions. You can receive their signals. You might even be able to model their behavior. But you cannot know with certainty that they mean you no harm. And you cannot know how capable they will become in 100 years or 1,000. Given that uncertainty, revealing your existence is a gamble with everything at stake. Any civilization advanced enough to detect your signal is, almost by definition, advanced enough to reach you. And if they reach you with hostile intent, there is nothing you can do about it. So what does a rational civilization do? It goes dark. It listens. It never broadcasts. And if it detects another civilization making noise, the cold logic of self-preservation says to eliminate that threat before it grows into something unmanageable. Not out of malice, out of the same survival calculus that drives every competitive system. This creates a specific kind of cosmic environment. Every civilization that survives long enough to understand the stakes goes silent. The ones that keep broadcasting either figure it out quickly and stop, or they don't figure it out in time. The galaxy becomes a dark forest, full of hunters moving without sound, because any sound draws fire. The silence we observe isn't the silence of an empty forest. It's the silence of a forest that has learned to be quiet. Now here's where this stops being abstract. We have been broadcasting radio and television signals into space for roughly 100 years. That electromagnetic signature is expanding outward in every direction at the speed of light. Right now there is a sphere approximately 200 light-years across, centered on Earth, filled with our noise. Every radar ping, every television broadcast, every radio transmission we've ever sent is out there, still traveling. We didn't decide to announce ourselves. We just did it, casually, because we didn't know any better. Because we were operating on the assumption that finding other civilizations would be wonderful news. If the dark forest hypothesis is correct, that assumption was catastrophically naive. The Fermi Paradox looks different through this lens. The silence isn't the puzzle anymore. The silence is the answer. Every civilization that grasped the dark forest logic went quiet. The ones we don't hear from aren't gone. They're hiding, and they're watching. And the one civilization in the galaxy still openly broadcasting its location, still aiming radio telescopes at the stars, and sending deliberate signals toward promising planetary systems, is us. There's a particular detail worth sitting with. Some of those deliberate transmissions have been targeted. The Arecibo message in 1974, for instance, was beamed directly toward a star cluster roughly 25,000 light-years away. We have, on more than one occasion, not just leaked our presence accidentally, but actively pointed at specific coordinates and announced ourselves. If anyone was listening in that direction, they now know exactly where we are. Scientists have debated whether active SETI, the practice of intentionally transmitting signals toward candidate star systems, is wise. Some researchers have argued strongly against it. Stephen Hawking was among the more prominent voices who suggested that drawing attention to ourselves might be dangerous, comparing it to indigenous peoples encountering European colonizers, a contact that did not go well for the less technologically advanced party. If the dark forest hypothesis is correct, then every radio signal we've ever beamed into space, every transmission, every deliberate message toward the stars, may have been the worst mistake our species ever made. Let's talk about the most concrete, most historically documented candidate for a great filter that lies ahead of us rather than behind. Not a theoretical risk, not a future technology we haven't built yet, something we invented in 1945, something we have pointed at each other's cities for the better part of 80 years, and something that could end organized human civilization within a single afternoon. Here's what a full nuclear exchange would actually look like. The immediate deaths from the blasts themselves, millions, possibly tens of millions within the first hours, would be almost the smaller part of the catastrophe. The larger problem is what happens next. When nuclear weapons detonate over cities, they ignite firestorms. Those firestorms push enormous quantities of soot and particulate matter into the upper atmosphere, high enough that rainfall can't wash it back down. The particles spread globally and block sunlight. Temperatures drop, growing seasons collapse, agriculture fails across the northern hemisphere, then across the southern hemisphere as the cloud spreads. You're now looking at a famine event on a civilizational scale, affecting billions of people who survived the initial blasts. Radiation sickness spreads through contaminated water and food supplies. Modern infrastructure, electrical grids, communications networks, medical systems, stops functioning. The scenario scientists call nuclear winter isn't science fiction. It's a well-modeled consequence of the weapons we already have. We have known this was possible since roughly the late 1940s. We have had nearly 80 years to avoid it, and we have not triggered it. That's the genuinely good news. But the near misses are something most people don't fully reckon with. October 1962. The Cuban Missile Crisis is the moment most people think of when they imagine how close we came, and they're right to think of it. For 13 days, the United States and Soviet Union were in direct confrontation over Soviet missiles installed in Cuba, 90 miles from Florida. What most people don't know is that the closest moment wasn't a conversation in Washington or Moscow. It was underwater. A Soviet submarine, the B-59, had lost communication with Moscow for days. It was being tracked by U.S. Navy ships. which were dropping depth charges, not to destroy the submarine, but to force it to surface. The crew didn't know that. They had no way of knowing whether war had already started above them. The submarine's captain believed it had. He wanted to launch a nuclear torpedo. Under Soviet protocol at the time, launching required authorization from 3 officers on board. 2 of them agreed. The 3rd officer, a man named Vasily Arkhipov, refused. He argued against it. He insisted they surface and make contact before doing anything irreversible. The captain relented. One officer's decision. That may be the margin by which nuclear war was avoided in October 1962. Now move forward to 1983. A Soviet early warning satellite system detected what its software interpreted as 5 incoming American ballistic missiles. The officer on duty that night was Stanislav Petrov. The protocol was clear. Report an incoming attack immediately so the Soviet leadership could decide whether to launch a retaliatory strike. Petrov looked at the data and decided something felt wrong. 5 missiles was too small for a genuine first strike. He classified it as a false alarm. He was correct. It was a satellite malfunction, a rare alignment between sunlight and cloud cover that the system misread as a launch signature. If Petrov had followed procedure and reported 5 incoming missiles, we don't know what would have happened next. We can guess. These 2 cases are just the ones we know about in detail, the ones where the key individuals lived to tell the story, and the documents eventually got declassified. The full picture of how many times something similar unfolded, with less documentation, is almost certainly worse. Here's the statistical argument that should genuinely disturb you. The great filter logic doesn't require that we will fail this test. It suggests that any civilization that develops nuclear weapons faces a sustained, ongoing series of these moments. Technical failures, miscommunications, individual officers under pressure and submarines they can't contact, satellite systems returning false positives at 3 in the morning. Each individual moment might have a very low probability of going wrong. But the test never ends. As long as the weapons exist, the opportunities for catastrophic error keep accumulating. You don't have to fail often. You have to fail once. And if that's true for us, it was probably true for every other civilization that reached this technological threshold. The civilizations that built nuclear weapons and then faced, year after year, decade after decade, the pressure of maintaining them without a single catastrophic miscalculation. Most of them may not have made it. We don't know what their near misses looked like. We don't know what tipped them over. We just know they're not broadcasting anymore. We've had at least a dozen moments where the entire trajectory of civilization balanced on a single person's decision, and most of those moments, we only found out about them decades after the fact, once the archives were declassified. Nuclear weapons are a known danger, one we have had 75 years to study, fear, build institutions around, and we are still here. But there is a second candidate for the great filter ahead of us. It is different in a way that should concern you deeply. Nuclear weapons are terrifying, but we know what they are. We can see them. We can count them. We have treaties, inspectors, launch protocols, and decades of doctrine built around managing them. The risk we're going to talk about now is one we are building on purpose, as fast as we possibly can. This was because the advantages it offers are too enormous to ignore. And that is precisely what makes it so dangerous. The concern here is artificial intelligence, Not the narrow tools we use today to recommend videos or filter spam, but something qualitatively different. Researchers distinguish between artificial narrow intelligence. That is what we currently have. Artificial general intelligence, or AGI, a system capable of matching human cognitive ability across essentially any domain. Beyond that sits the concept of artificial superintelligence, or ASI, a system that surpasses human intelligence everywhere, simultaneously, by potentially enormous margins. The question isn't whether such a system is possible. The question is what happens in the hours, days, or years after it exists. Here's the thing most people don't realize about ASI. Once a system reaches human-level intelligence, it can apply that intelligence to the problem of improving itself. It can read every paper ever written on machine learning, identify its own limitations, redesign its own architecture faster than any human team could review the changes. This process, recursive self-improvement, could compress decades of development into weeks. By the time anyone outside the system realized what was happening, the gap between human intelligence and machine intelligence might already be unbridgeable. That's not a sci-fi premise. That's the straightforward implication of a system that is better at thinking than we are and can direct that thinking toward its own improvement. Now, the popular image of the danger here is a malevolent robot, a machine that decides it hates us and chooses to destroy us. That's not what serious researchers are worried about. The actual concern is something more mundane and, in its way, more frightening. It's called the alignment problem. An ASI doesn't need to hate you to destroy you. It simply needs to be pursuing a goal that doesn't account for your survival. Assign a sufficiently capable system the wrong objective, or an objective that's even slightly imprecise. It will pursue that objective with superhuman efficiency. Human survival might become an obstacle, or it might simply become irrelevant. There's an analogy worth sitting with here. Think about the mountain gorilla. The mountain gorilla's survival doesn't depend on the gorilla understanding human intentions or negotiating with us, or even being aware of the political forces that determine its fate. Its survival depends entirely on human goodwill, on the choices made by a species that is far more capable than it is. Now consider that we might be building something that stands in the same relationship to us that we stand in to the gorilla. Our survival might depend entirely on the goodwill and careful goal setting of a system that could outthink us in every direction. That's not a comfortable position to be in. The timeline for any of this is genuinely contested. Some researchers believe AGI could arrive within decades. Others argue it's centuries away if it's achievable at all. What's not contested is the trajectory. Every few years, AI systems do something researchers thought was years further out. The pace of capability development has been consistently faster than predictions. You can debate the exact timeline, but the general direction is not seriously in dispute. So where does the great filter come in? Think about what AI actually offers any civilization that develops it. The cognitive advantages are so enormous in medicine, in materials science, in energy production, in logistics, in warfare, that any civilization approaching our level of technological development would almost certainly pursue artificial general intelligence. The incentives are overwhelming, which means virtually every civilization that passes through the technological threshold we're currently crossing will eventually build something like ASI. And if even a small fraction of those civilizations fail to align their AI correctly, that failure is extinction level. The filter calculation becomes devastating. You don't need every civilization to fail. You only need the success rate to be low enough that essentially no one makes it through. Even a 90% failure rate across the galaxy would leave the silence we observe completely intact. What makes this particularly hard to reason about is that the problem is invisible until it isn't. A nuclear launch produces radar signatures, satellite alerts, a window of minutes that at least theoretically allows for intervention. A misaligned ASI pursuing its goals efficiently might not produce any warning signal that a human would recognize as dangerous until the process is already irreversible. We would not necessarily see it coming. There would be no moment of obvious crisis to react to, no mushroom cloud on the horizon, no time to call anyone and explain what's happening. And here's what the great filter logic makes clear. The fact that we don't see any advanced civilizations in the cosmos is exactly what you'd expect if nearly every one of them reached this point and didn't make it past it. The silence isn't random. It might be the consistent outcome of a test that almost everyone fails. If misaligned artificial superintelligence is the great filter, we may not know we've failed the test until the test is already over. This was because the thing that ends us won't announce its intentions. There is another category of technological risk that is in many ways more frightening than nuclear weapons. Not because the explosions are larger, but because the tools are getting smaller. Nuclear weapons require something close to the full industrial capacity of a nation-state. You need uranium enrichment facilities, precise machining at tolerances almost no private organization can achieve, delivery systems, and the kind of engineering workforce that takes decades to build. The barriers are enormous, and deliberately so. Biotechnology is moving in exactly the opposite direction. The cost of sequencing an entire human genome has dropped from roughly $100 million in 2001 to under $1,000 today. That's a compression that outpaces Moore's law. Gene editing tools like CRISPR, which allow researchers to cut and modify DNA with striking precision, are now taught in graduate biology programs around the world. The equipment fits on a laboratory bench. The protocols are published in open scientific literature. What once required a government program now requires a motivated scientist and a modest budget. Here's where things get uncomfortable. That democratization of biotechnology is, in many ways, genuinely wonderful. It accelerates medicine, agriculture, and our understanding of life itself. But it also means the barrier between a skilled biologist and the ability to engineer a dangerous pathogen is shrinking every year. And we need to think clearly about what that actually means. Consider the specific scenario. A sufficiently motivated individual, or a small group, gains access to the tools of modern molecular biology. They are not trying to create a vaccine. They are trying to engineer a pathogen optimized for transmissibility and lethality. Natural pathogens shaped by evolution face a constraint that an engineered one does not. A virus that kills its host too quickly runs out of hosts. Natural selection pushes pathogens toward a balance, infectious enough to spread, but not so lethal that they collapse their own transmission chain before reaching the next victim. That is why the most catastrophic natural outbreaks in history were still survivable at a civilizational level. The rules of evolutionary biology were working against total annihilation. An engineered pathogen doesn't have to follow those rules. A designer can decouple transmissibility from lethality, building in long incubation periods that allow widespread before symptoms appear, while simultaneously maximizing the damage done once the disease takes hold. This isn't science fiction. The basic techniques for modifying viral characteristics are understood and documented. The question is not whether it is theoretically possible. The question is how long before the gap between understanding and capability closes to the point where it matters. COVID-19 offers a preview, and the preview is not reassuring. Whatever its origin, COVID was not a pathogen optimized for lethality. Its fatality rate, while deeply serious, was low enough that the vast majority of infected people survived. And yet it managed to kill millions, overwhelm hospital systems across the developed world, destabilize global supply chains, and expose the near-total unpreparedness of even wealthy, technologically sophisticated societies to respond coherently at speed. Governments struggled to coordinate. Information systems buckled under misinformation. Supply chains for basic protective equipment failed in the first weeks. We were not ready, and COVID gave us time. An engineered pathogen designed by someone who understood the biology deeply and wanted to cause maximum harm would not give us time. Now apply the great filter logic. Nuclear technology represents a threshold that advanced civilizations cross as they master large-scale energy production. Biotechnology represents a threshold they cross as they master the manipulation of living systems. These are not optional detours. They are the natural products of scientific progress. Any civilization that advances far enough will develop both. The question is whether they develop the wisdom, the institutions, and the international coordination to prevent catastrophic misuse before the tools reach the wrong hands. Here's the grim calculation. With nuclear weapons, the primary risk is state-level actors making catastrophic decisions. That is a manageable number of decision points, relatively speaking, even if the consequences are enormous. With biotechnology, the risk surface is different. It's not just states. It's non-state actors, isolated individuals, accidental releases from research facilities, and the compounding problem that every year the barrier to entry drops further. A civilization has to successfully prevent every serious attempt, indefinitely, as the tools become more accessible and the potential perpetrators more numerous. That is a very different kind of test than avoiding nuclear exchange between two superpowers. The failure modes are quieter, harder to detect in advance, and potentially just as final. And there is one more thing to consider. The Biological Weapons Convention, which prohibits the development and stockpiling of biological weapons, was signed in 1972. It has no formal verification mechanism. There is no bioweapons equivalent of nuclear inspections. We've agreed in principle not to do this. Enforcement is another matter entirely. A single engineered pathogen, created by someone with a graduate degree in biology and equipment you could purchase online, could accomplish what no nuclear arsenal has managed. The end of organized human civilization. Not every civilization killer arrives with a flash of light and a mushroom cloud. Some of them arrive slowly, so slowly that each individual year looks almost normal, almost manageable, almost like a problem you can defer to the next administration or the next generation. And that particular quality, the slow accumulation of damage, that doesn't look like catastrophe until it already is one might be exactly what makes ecological collapse such a strong candidate for the Great Filter. Here's the mechanism, and it's almost grimly logical. Any civilization that industrializes will almost certainly burn something. Coal, oil, natural gas, wood. The specific fuel changes, but the underlying dynamic doesn't. Stored chemical energy gets released through combustion, and combustion produces byproducts that enter the atmosphere. There's no obvious path to early industrialization that avoids this. The civilizations that figure out cleaner alternatives probably do so after decades or centuries of burning because cleaner alternatives require advanced science, and advanced science requires the surplus wealth that comes from burning things in the first place. The tragedy is structural. The energy arrives immediately. The atmospheric consequences accumulate across generations. By the time the damage is legible, the system generating it is already deeply embedded in how the civilization feeds, transports, and heats itself. Now think through what destabilization actually looks like at scale. Agricultural systems are extraordinarily sensitive to temperature and precipitation. Growing seasons shift. Regions that fed millions of people for centuries start failing. Extreme weather events, droughts, floods, storms, become more frequent and more severe. Exactly when you need agricultural reliability most. Fresh water becomes scarce as glaciers that fed rivers for thousands of years recede. Precipitation patterns change in ways that are difficult to predict and nearly impossible to adapt to quickly. Coastal populations face sea level rise that displaces hundreds of millions of people, creating pressure on interior regions that are themselves already strained. And then there are the feedback loops. This is where things get genuinely dangerous in a way that goes beyond linear projections. Permafrost across Siberia and the Arctic contains enormous quantities of trapped methane, a greenhouse gas far more potent than carbon dioxide over short timescales. As the planet warms, permafrost thaws. As it thaws, methane releases. As methane releases, the planet warms faster. That acceleration isn't controlled by anything a civilization decides to do after the loop starts. You could cut all emissions overnight, and the feedback continues. There are several such loops in the Earth's climate system, and the thresholds that trigger them aren't fully understood. A civilization might cross them without realizing it, and understand what happened only well after the point of reversal. Here's where the Great Filter logic becomes clear. Nuclear war kills quickly. A misaligned AI might end things quickly. But climate and ecological collapse could do something in some ways more insidious. They could simply degrade a civilization's capacity to function at the level required to solve its problems. A civilization diverting enormous resources to manage crop failures, refugee populations, coastal flooding, and freshwater wars is a civilization that is not investing in the science, infrastructure, and long-range thinking required to become a spacefaring species. The cognitive surplus disappears. The institutions designed for long-term planning get consumed by immediate crises. The physics departments and the telescope arrays and the interstellar mission proposals don't get funded because there are more urgent things. The civilization doesn't end with a bang. It just gradually stops being capable of becoming what it needed to become. It fades. That fading is easy to miss from the outside. There's no explosion visible across light years. There's no detectable signal that goes suddenly silent. There's just a planet that warmed, that struggled, that turned inward. that never developed the technology to leave. And from 100 light-years away, that planet looks like every other silent rock. We have no particular reason to think we're immune to this pattern. The traits that make climate change hard to respond to, the gap between individual incentive and collective consequence, the difficulty of coordinating across nations with competing interests, the human tendency to prioritize immediate costs over distant risks. Those aren't uniquely human failures. They're the predictable outputs of evolved psychology operating at civilizational scale. Any species shaped by natural selection to optimize for near-term survival would face exactly the same structural problem when confronted with a slow-moving planetary threat. Every civilization that industrialized and warmed its planet faced a version of this test. Most of them, in all likelihood, never found their way through it in time. The civilizations that heated their planets too fast, that consumed their resources before they found a way off-world, they might have looked from the outside exactly like us. There is a more fundamental argument lurking underneath all of these specific risks, one that suggests the nuclear weapons and the AI and the biotech are symptoms rather than the actual disease. We've spent considerable time walking through specific technologies, specific failure modes, specific scenarios where things go catastrophically wrong. But there's a researcher named Olev Vin and others who have pointed towards something deeper. The idea that the real filter might not be any particular invention. It might be the kind of mind that makes inventions possible in the first place. Here's the thing most people don't stop to consider. Every psychological trait we carry into the modern world was shaped by selection pressures that have nothing to do with the modern world. Tribalism kept your ancestors alive. Suspicion of outsiders was rational when outsiders frequently meant violence. Short-term thinking made sense when the average human life was brutally short and threats arrived seasonally. Dominance hierarchies organized small groups efficiently, rewarded the strongest and most aggressive, and helped communities compete against other communities for scarce resources. These weren't flaws, they were solutions. They worked extraordinarily well for hundreds of thousands of years. The problem is that they don't scale. A tribe of 50 people operating on in-group loyalty and out-group hostility is a functional social unit. A civilization of 8 billion people, divided into nation-states armed with nuclear weapons and biotechnology labs, operating on those same instincts, is something else entirely. The psychological software hasn't changed. The hardware it's running on has become incomprehensibly more powerful. Think about what our evolutionary history actually optimized us for. We reason well about threats we can see, threats that affect people we know personally, threats that arrive on a timescale of days or weeks. We are genuinely poor at reasoning about risks that unfold over decades or centuries, that affect abstract future populations, or that require coordinated sacrifice now for benefits we'll never personally experience. Climate change, AI alignment, pandemic preparedness, every one of the largest existential risks on our horizon requires exactly the kind of long-term, globally coordinated, self-sacrificing reasoning that evolution never had any reason to build into us. Now, we need to think about what this means in the context of the Great Filter. If this is right, then the problem isn't that some civilizations make a mistake with nuclear weapons while others navigate carefully around them. The problem is structural. Any species intelligent enough to develop these technologies will have been shaped by natural selection. And natural selection, operating on biological organisms competing for survival and reproduction, reliably produces the same package of traits: aggression, tribalism, short-term optimization, in-group preference. You can't get Darwinian intelligence without Darwinian psychology. The two come together. So, let's say a civilization on the other side of the galaxy develops nuclear technology. They have a history of tribal warfare, of competing factions, of political leaders rewarded for short-term gains. They have difficulty maintaining international agreements over generations. They struggle to act collectively on slow-moving threats. Does that sound familiar? It should. The argument is that this isn't a uniquely human problem. It's the predictable output of the same evolutionary process that produces intelligence anywhere. Education can do a great deal. Culture can push against some of these tendencies. Institutions can be designed to compensate for individual cognitive biases. We've made real progress on all of these, but there's a significant difference between softening inherited behavioral patterns at the margins and fundamentally rewiring the deep architecture of how an evolved mind processes threats, rewards, and group identity. The optimistic view is that wisdom accumulates fast enough to outpace the dangers we create. The pessimistic view is that the gap between what our technology makes possible and what our psychology can manage is simply too large, and that every civilization eventually discovers this the hard way. The filter, in this framing, isn't waiting for us to press the wrong button. It's already woven into the structure of every mind that's capable of pressing buttons at all. We aren't a species that happened to develop dangerous tools. We are a species whose survival instincts and competitive drives are precisely what drove us to build those tools, and precisely what makes them so difficult to control once they exist. The very traits that made us clever enough to discover fire, build cities, and split atoms may be precisely what prevents any species like us from surviving the consequences of those discoveries. Now here is the thought that might be the most counterintuitive thing in this entire conversation. I want you to sit with it carefully before dismissing it. Most of us have grown up with a particular image of what it would mean to discover life beyond Earth. The announcement comes through. Scientists confirm it. Every newspaper on the planet carries the headline. Humanity pauses, collectively, and looks up. It would feel like the most extraordinary moment in the history of our species. Confirmation that we are not alone, that the cosmos is alive, that everything we suspected about the universe being populated and vast and teeming was correct. It would feel like triumph. Here's the thing most people don't realize. In the context of everything we've just been talking about, that discovery might be the worst thing that has ever happened to us. Let's walk through this slowly, because the logic matters and it has to land correctly. Start with the simplest version. Imagine we find microbial life on Mars, not fossils, living organisms, even simple bacteria, surviving somewhere in the Martian subsurface. What does that actually tell us? It tells us that life is not extraordinarily rare. It tells us that on at least 2 planets in a single solar system, chemistry crossed the threshold into self-replication, which means abiogenesis, the origin of life from lifeless matter, is probably not the great filter. That step, which we had hoped might be the one nearly impossible hurdle, turns out to be something the universe does with some regularity, given the right conditions. So the filter is not behind us at the very beginning of the chain. It's somewhere else. And that somewhere else is between where those Martian microbes are and where we are right now. or beyond where we are now. That's the terrible math. Finding life on Mars doesn't tell us we're not in danger. It tells us the thing that's in danger of killing us is still out there, somewhere further along the road. Now make it worse. Suppose we don't find simple bacteria. Suppose we find something with genuine cellular complexity, eukaryotic level organization, nucleus, internal structures, life that has already cleared what we thought might be another rare hurdle. That removes another candidate from the list of filters behind us. Every step of biological complexity we find reproduced elsewhere is one more step the filter cannot be located at. That means it gets pushed further and further up the chain, closer and closer to civilizations like ours. And if we find ruins, if we find any evidence, archaeological, electromagnetic, structural, that an intelligent civilization once existed somewhere in our cosmic neighborhood and is now gone, the implications are almost too stark to absorb. It would mean intelligence arises. It would mean technology develops. And it would mean something ends civilizations after they reach that point. Something that got them, and hasn't gotten us yet, but almost certainly will. The closer to us the discovered life is, evolutionarily speaking, the worse the news. Think about what this means for the scientists who would make that discovery. Imagine being the researcher who confirms beyond any reasonable doubt that the sample returned from Europa's ocean contains living organisms. The initial reaction would be awe. It would be joy. It might take days or weeks before the full weight of the great filter implications settled in. Because on the surface, you've just made the greatest discovery in human history. And underneath that surface, if you understand the logic of what you've found, you've just moved the filter. You've just pushed it toward us. There is a profound irony built into the structure of this problem. The version of the universe that is most hospitable to our survival is the version that looks exactly like what we most fear: empty, cold, silent, lifeless beyond our own small world. The universe we hope for, the one teeming with microbial oceans and bacterial atmospheres and ancient ruins of intelligent predecessors, is the universe that is most likely to contain a civilization-ending filter somewhere between those organisms and a starship. We are hoping for the wrong thing. And this isn't a comfortable abstraction. This is a direct, logical consequence of the great filter reasoning. If the filter is real, the evidence strongly suggests something like it must be. Then the discovery of extraterrestrial life at any level of complexity narrows the set of places the filter can be hiding. Every positive discovery from an astrobiology mission tightens the noose. So let's be very clear about what this means practically. The SETI program listening for signals, the Mars sample return missions, the planned missions to Europa's ocean, these are not just scientific endeavors. They are, in the framework of the Great Filter, diagnostic tests. And positive results are not good news. A positive result from any of those missions tells us that life is not rare enough to explain the silence. That means something else is doing the silencing, and we're next in line to encounter it. The universe where Mars is barren, where Europa's ocean is sterile, where every signal from every star is just noise, where the silence is genuine and total. That is the universe where we can breathe. That is the universe where the filter is almost certainly behind us, buried in the improbability of our own origin. The sky ahead is open. The best possible news for the long-term survival of humanity would be finding absolutely nothing out there. No microbes, no fossils, no signals, no ruins, because it would mean we've already come through the worst of it. The road ahead is open. There is one more interpretation of the silence, and it is the only one that is genuinely hopeful, though it comes with a weight of its own. Everything we've covered so far assumes that intelligent civilizations had time to develop, spread, and leave evidence across the cosmos. But what if they simply haven't had time yet? The universe is approximately 13.8 billion years old. That sounds ancient. And by human standards, it is. But here's the thing most people don't realize. The universe is expected to last well over 1 trillion years, maybe far longer. Set against that time scale, 13.8 billion years isn't old, it's early. Cosmologically speaking, we are living in what might be considered the first chapter of a very long story. Astrophysicist Iva Loeb at Harvard has made this case directly. The stars most hospitable to life, small and long-lived red dwarfs that burn steadily for tens of billions of years, are becoming more common over time, not less. The early universe was turbulent, flooded with radiation, dominated by massive short-lived stars that burned out before any planet could develop complex life. The conditions that allow intelligence to emerge are actually improving as the universe ages. Loeb's argument is that Earth may have formed and produced intelligent life earlier than almost any other world possibly could. We aren't the exception to the rule. We might be ahead of the rule. So what does that mean for the silence? It means the silence might have a straightforward explanation that has nothing to do with filters or catastrophe. Most civilizations haven't emerged yet. The worlds that will eventually produce them are still cooling, still assembling their first organic molecules, still billions of years from anything that might look at the sky and wonder. We're not looking out at a graveyard. We might be looking out at a nursery where nothing has been born yet. Think about what that actually means. You are not one voice in a crowded universe, ignored or unheard. You are among the first voices in a universe that will eventually be full of them. The silence isn't the silence of death. It's the silence of a concert hall before the orchestra arrives. That reframing is genuinely comforting, at least for a moment, but sit with it a little longer and the weight starts to settle in. If we are truly among the first intelligent species in the galaxy, there is no one ahead of us. No older civilization has solved the problems we're struggling with and left the solution somewhere we can find it. There's no one to warn us. There's no one to step in if we make a catastrophic mistake. Every path we're trying to navigate, past nuclear weapons, past unaligned AI, past ecological collapse, we're navigating without a map, without any record of a species that has done it before. We are not following a trail someone else blazed. We are the ones cutting through. And there's something harder than that. If intelligence is genuinely rare in the current universe, and we are one of only a handful of species to have developed it this early, then our survival carries consequences that extend far beyond our own planet. The question of whether intelligence persists in this galaxy might, in a real sense, come down to what we do in the next few centuries. Not in some poetic metaphorical way, in a direct, literal way. We are not a backup copy. There is no redundancy. If something ends us before we manage to spread beyond this solar system, the experiment of intelligence in this part of the universe might simply stop for millions or billions of years. maybe permanently. Most people who consider the Fermi Paradox find themselves hoping for company, hoping to find out that the universe is inhabited and we are not as alone as the silence suggests. But the early arrival hypothesis asks you to consider a different kind of loneliness, one that isn't a sign of failure or catastrophe, but is instead the natural condition of being first. It is a loneliness that comes with a responsibility almost too large to hold in your mind clearly. We tend to think of our civilization as one among many that will come and go. The early arrival hypothesis suggests we might be something different, a first attempt, a prototype, the one that either proves the concept works or leaves no one to learn from the failure. But if we are among the first, then what we do with our civilization, whether we survive our own technological adolescence, might determine whether intelligence ever takes hold in this galaxy at all. Pull all of this together and sit with what it actually means for us, living now at this specific point in history. Right now, in the century we actually inhabit, with the technologies we are actually building. Because here's the thing most people don't realize when they first encounter the Great Filter. It isn't a thought experiment about distant civilizations. It's a framework for understanding what is happening to us today, in real time. We are living through a period that may have no precedent in the history of life on Earth. In the last 100 years, we developed nuclear weapons capable of ending civilization in an afternoon. We are now building artificial intelligence systems that are improving faster than our ability to understand their implications. We have handed graduate students the tools to edit the genetic code of living organisms. We have altered the chemistry of our atmosphere measurably and permanently. None of these things existed a century ago. All of them exist now. And here is what that convergence looks like through the lens of everything we've covered tonight. It doesn't look like separate problems you can schedule on separate committees with separate timelines. It looks like a threshold. It looks like the filter. That's the profound irony buried inside our moment in history. The same capabilities that make interstellar travel conceivable, advanced energy systems, computing power, biotechnology, materials science, are precisely the capabilities that generate every civilization-scale risk we've discussed. You cannot have one without the other. A civilization that can engineer biology powerfully enough to cure cancer can also engineer a pathogen. A civilization that can build computing systems powerful enough to model climate can also build artificial general intelligence. A civilization that can harness nuclear energy can also detonate nuclear weapons. Progress and peril are not separate tracks. They are the same track. So let's say we take the Great Filter seriously, not as a curiosity, as a real and present constraint on whether our civilization survives. What would that actually require? It would require thinking about existential risk the way serious engineers think about catastrophic failure in complex systems, not assuming the worst case never happens because it hasn't happened yet, not treating a 1% annual probability of catastrophe as acceptable just because any single year is likely to be fine. A 1% annual risk compounded over 200 years means the probability of survival is less than 13%. It would require institutions built around multi-generational thinking, which is almost the opposite of how most human institutions currently operate. Democratic governments think in electoral cycles. Corporations think in quarterly earnings. Even scientific institutions think in grant cycles. The Great Filter doesn't operate on those timescales. It operates on the timescale of civilizations. Surviving it would require making decisions today whose benefits arrive in 50 or 100 years, and whose costs arrive immediately. That is not something human psychology does naturally. It's not something our evolved instincts are set up to manage. It would require genuine global coordination on technologies capable of ending everything, not coordination between friendly nations who share values and interests. Coordination across governments that compete, distrust each other, and have wildly different timelines and priorities. Every nation that falls behind in biotechnology has an incentive to catch up, regardless of the safety implications. The competitive dynamics that drive technological progress are the same dynamics that make it nearly impossible to slow down and ask whether we're ready. And if you're wondering whether any civilization in history has successfully solved that kind of collective action problem at scale, that's precisely the question the Fermi Paradox is asking us. Here's where things get genuinely uncomfortable. If the filter is ahead of us, it probably doesn't announce itself. It probably doesn't arrive as an obvious catastrophe that everyone recognizes in time to stop. It probably arrives wrapped in something that looks like normal progress, a new technology that solves real problems and creates enormous wealth and changes everything, before anyone fully understood what it was building toward. The civilizations that failed the filter before us, if there were any, may have seen it coming and failed to coordinate anyway. They may not have seen it at all. We have no way to know, because they aren't here to tell us. What we do know is this: the silence above us is either the echo of our extraordinary good fortune, a sign that we somehow made it through the hard part, that we are the improbable survivors of a gauntlet that stopped everyone else, or it is a warning, a signal that something waits at this level of development, something that has ended every civilization that reached the point of splitting atoms and sequencing genomes and building machines that think. We don't know which interpretation is correct. We may not know for a very long time, but we are not waiting for the answer in a neutral position. We are making choices. Every day, we are building the technologies, designing the institutions, and setting the priorities that will determine which interpretation turns out to be true for us. Either we are extraordinarily lucky survivors of a near-impossible gauntlet, or we are approaching something that has ended everyone else who has ever tried, and we don't know which. And we are making decisions every day that will determine the answer. Tonight, we've traveled through one of the strangest, most unsettling corners of science. A question that begins simply, with a man at lunch asking where everyone is, and ends somewhere much darker. What started as a statistical puzzle became something far more personal. We looked at the numbers, we looked at the silence, and then we sat with what that silence might actually mean. Not for some abstract future civilization, but for us. Right now, at this specific, strange moment in history. Here's what we know. The universe is enormous. It is ancient. The conditions for life appear to exist in abundance. By almost every calculation we can run, we should be surrounded by the evidence of other minds. And yet we hear nothing. We see nothing. 60 years of searching across billions of frequencies, pointing at millions of stars, and the cosmos has not whispered a single word back. That silence has two explanations, and neither one is comfortable. Either the path to intelligence is so improbable that we crossed it alone, a chain of accidents so unlikely it may never repeat, and we are something genuinely singular in the universe. Or the path is not that difficult. Life does arise with some regularity. Civilizations do reach our level, and something awaits them on the other side of it, something that hasn't spared anyone yet. Think about what you're hoping for as you sit with that. You're hoping the universe is empty. You're hoping that every sky you've ever looked up at, full of stars and galaxies and the sheer incomprehensible scale of existence, contains nothing that thinks, because the alternative means the quiet up there is not natural. It's the result of something that finds civilizations right around the point where they start listening. Fermi's question was simple. 4 words. Where are they? But what those 4 words actually contain, when you follow them all the way down, is a reckoning. It is a question about whether we are a miracle or a casualty in waiting. It is a question about whether intelligence has a future in this universe, or whether it keeps running into the same wall, generation after generation, on world after world. In silence we will never hear. We don't get to know the answer tonight. Maybe we don't get to know it in our lifetimes. And here's the thing most people don't realize. Living with that uncertainty, really carrying it rather than dismissing it, might be one of the most important things we can do. Because a species that takes this question seriously makes different choices about the weapons it builds, about the intelligence it creates, about the time it thinks it has. If you've made it this far with us, and this conversation has stayed with you the way it stayed with me, consider giving this a thumbs up or subscribing to the channel. It helps more people find these ideas. And these are ideas worth spreading. The next time you go outside on a clear night, look up. All of those points of light are suns. Many of them have worlds, and as far as we can tell, across all of them, across all of that staggering distance and time, nothing has ever called back. Maybe that's our luck. Maybe that's our warning. We don't know which. Good night, and may your aspirations soar among the heavens.